MapReduce in 10 minutes. Let's go! My name is Evan Smith. I'm on Twitter and I have a very low activity blog. I really enjoy connecting with folks, so feel free to look me up and reach out. We're really here to talk about MapReduce though. So map and reduce are individual words that have definitions. We'll talk about what they kind of mean in functional programming and then how they allow us to process big data in an efficient way. Functional programming is a programming paradigm that they call declarative, and that's as opposed to imperative statements. One of the main goals of functional programming is to not alter a business object's state. We would really not ever take an object, do something to it, and then use that object again. What we would do is take an object into a function, do some stuff, and give you a new object. So what this really requires you to do in functional programming, or it rather encourages you to write simpler functions that can be reused and then compose multiple functions to get your desired output. Map simply means to filter and sort. And I think that's the end of the talk. Just kidding. So we have all these Scrabble pieces, and there's not a lot we can do with them in this state. We need to organize this chaos. So what map would do is it would go through each letter in the pile of Scrabble tiles. It will give you what I would call a dictionary, but it will give you this listing of here's A, and here's how many A's there were. Here's B, and here's how many B's there were. So we got 2 A's, 6 B's, 2 C's, 2 D's, whatever. I mean, this is the output of the map function. So it takes a scrabbled, I guess, mess of tiles there and maps them out so you know what you have. I will say, for those of you who already know what map and reduce do or are familiar with functional programming, this isn't 100% accurate. Now, really this looks like the result of a map and a reduce, but here's the difference. Map is going to map each letter out into its own element. So really, instead of A, 2, you would have A, right? Well, I didn't really want to show it that way. So we'll say, for our purposes, that we know that a map gives you A, B, 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 C, C, D, D, yada yada, right? Map takes the pile and separates the letters out. But I did want to illustrate here that there's 2 A's. So say that we have 2 of these piles of Scrabble tiles, and we're going to map them both, right? Well, now I have 2 separate result sets of A's, B's, C's, and all these. Well, that really seems like what I started out with originally, right? I have some things, but what I want to end up with is kind of a summary of those things, right? I want to know how many A's I have in total, not how many A's in pile 1 and how many A's in pile 2, because I have n number of piles of Scrabble tiles, and we need one listing instead of multiple listings. Well, that's where reduce comes in. So all reduce is going to do is just summarize, and it works really well with map, and that's why a lot of times you hear map and reduce together. It's just going to summarize the multiple listings we have from map. So how does it do that? So on the left side you can see that we have 3 different maps coming from 3 different piles of Scrabble tiles. We can reduce those into a single listing, right? And these are really key value pairs, right? You may have noticed from before, I was talking about a dictionary. Your key is your letter, and your value is the count of how many times that letter appeared in the pile. So when we have 3 collections of key value pairs, we want to reduce those into a single listing of key value pairs. So as you can see on the left side, we had 2 A's in the first one, 1 A in the second one, and no A's in the third one. Well, that reduces down to 3 A's because it just adds them up, right? Well, now we have to talk about how this is relevant in big data. So let's do that now. Big data is a thing, right? It's a problem to process so much data. If it's a data set that's larger than can fit on my laptop, then I'm surely not going to process it on my laptop. So we got to figure out how we're going to do this. You could get access to a supercomputer and have just amazing hardware packaged into one computer, but that's not really going to be cost effective for most people and organizations. So what we want to do is we want to distribute the compute across multiple different computers. So if you can visualize a situation where we got map and reduce that work together to filter and sort and summarize, that's what we're going to do with a distributed file system processing big data. If you can imagine a single pile of Scrabble tiles that is huge, we're going to split that single big pile into multiple chunks of data. Now, really your input could be a single huge chunk, or it could be several different streams of data that are coming into our processor here. But the concept is that in any case I can split into more manageable chunks of data. Let's say that I was using 3 of my laptop to process my data. I could split the data into chunks that were sized for my laptop. Each of my laptops are going to do a map operation. In the context of big data, a lot of times what we do is we shuffle that. So we take the result of those maps, we got the key value pairs, A2, A1, and then no A. We're going to shuffle those 3 map results into a different structure here. We're going to say, okay, of my 3 map results, I've got A of 2, 1, and 0. B was 6, 0, and 8. It doesn't really matter which map or which split these came from. What matters is we're transforming the data that was in our original huge input that got split and mapped into a form that we're going to be able to easily reduce. Then once we've got it shuffled, we can reduce it into, well, what's the sum of my A's? Well, it's 3. What's the sum of my B's? It's 14, and so on. Each of the letters in the shuffle is kind of separate. Each of the letters in the reduce is separate. Well, your output combines everything in your reduce to be one set of key value pairs again. So your input is this jumbled mess. It's a ton of data. We can split it and process the map on different computers. So that's the distributed nature of the system. We shuffle those around, get them in an order that we can figure out. We reduce them, and then our output is the shape that we needed it to be. Here's a different example of it. Say we were doing some word count processing. We've got say the Internet Archive. So we're going to get a couple things out of this. Our process is going to give us an exhaustive list of all the words in the Internet Archive. It's going to give us a word count of each of those words. We start with this input, so we're just going to split those up in the algorithm split does not matter, but we're going to split them up in some manner. Here it's doing it by line. We're going to map these out. You see the first green box is kind of mapped into Deer 1, Bear 1, River 1. It's simply counting the different words there. It's just mapping them on a one-to-one basis. So then we go to shuffle that. It takes the result of all the mappings and combines them by word, right? And so that's going to be our key is the word, and then we'll have a list of counts. And so Bear 1, 1, etc. That's the orange boxes. We'll reduce that into Bear 2, Car 3, Deer 2, and River 2. It's red boxes, and then our final result is a list of the key value pairs. Alright, so how do I leave this talk and go implement MapReduce? What you would do is you would go out to Apache Hadoop, look at their implementation of MapReduce. MapReduce is algorithm. Hadoop is an implementation of that algorithm. Alright, so these resources will help you get started with Hadoop. The first one here is Hadoop documentation. The other place that I would go is IBM Analytics. In association with IBM, there's a website called cognitiveclass.ai. And then I found that on Talend, there's actually a pretty good article